Picture an elderly man, his hands trembling slightly, standing completely alone in a massive, dark, shadowy laboratory. The air in this room is heavy. It smells faintly of sulfur, metallic dust, and something sharply acidic. Decades of breathing in that atmosphere have left their mark. Lining the walls, from the floor all the way up to the ceiling, are meticulously labeled shelves holding thousands of glass bottles. Inside these bottles are the actual fundamental building blocks of the universe, purified, isolated, and categorized through decades of his own obsessive, back-breaking manual labor. It is the absolute pinnacle of human scientific achievement up to that exact point in history. An entire universe of matter wrestled into perfect order within one single room. But there is a profoundly heartbreaking twist to this scene. The man stares at the labels on the bottles. His mind, a mind that was once literally the most powerful and precise scientific instrument in all of Europe, is failing him. He squints at the faded ink, but he simply cannot remember what chemicals are actually inside the glass anymore. The immense order he spent his whole life imposing on the world is slipping right through his fingers. He is losing his own internal ledger. In an act of profound despair, he begins to take the bottles down, one by one. He is forced to systematically destroy his entire life's work. He uncorks them, dumps them out, and smashes the contents. He has to. The very elements he spent his whole life studying, the heavy metals, the toxic, invisible vapors, have slowly poisoned his nervous system. They have stolen his memory. It is a Shakespearean tragedy played out in a chemistry lab. The man who gave humanity the universal language to describe the physical world is left utterly without the language to understand his own legacy. Welcome to Legendary Lives Unveiled. If you are captivated by the hidden tragedies behind history's greatest minds, make sure to subscribe and like this video as we uncover the dark truths of the past. Today, we are taking a deep dive into the source material surrounding a life that completely rewrote the operating system of the physical sciences. The life of Jöns Berzelius. If you have ever written the chemical formula H2O, looked up at a periodic table hanging in a high school classroom, or simply used the word protein while reading a nutrition label, you owe a direct, unpayable debt to this man. To reconstruct his legacy, we are pulling from a fascinating stack of sources. Historical biographies of 19th century Swedish science, translated personal letters between Berzelius and his contemporaries, like Gerardus Mulder, modern chemical analyses of his original laboratory methods, and the wild archival records from the Royal Swedish Academy of Sciences. Our mission today is to unpack how an unwanted orphan, a boy who literally slept in unheated storage rooms and was dismissed by his own teachers as a complete slacker, rose to become the unquestioned dictator of European science. We will explore how his desperate, deep psychological need for control allowed him to revolutionize our understanding of matter, and how that exact same trauma eventually turned him into the greatest single roadblock to scientific progress in his entire era. The arc of his life is a perfect case study in how specific psychological wounds can shape the trajectory of global science. His brilliant obsession with order created modern chemistry, but his eventual inability to tolerate chaos almost completely broke it. The story of how Berzelius became a titan of logic starts in a place of absolute terrifying chaos. He was born on August 20th, 1779, in a tiny, deeply rural, and highly traditional parish called Väversunda in Sweden. He was born into a family with a long, heavily established line of clergymen. His father, Samuel Berzelius, was a teacher and a school principal. His mother, Lisbeth Dorothea, also came from a very prominent family of pastors. On paper, in 18th century Sweden, you would expect a comfortable trajectory into the church or theological academia. But the universe threw a massive wrench into that trajectory. His father died when he was only 4 years old, the first major fracture in his life. His mother remarried a local pastor to maintain domestic and financial stability, but then she fell ill and died when Berzelius was just 8. By the time he was a young boy, he was entirely orphaned, thrust into a reality where the adults who were supposed to protect him just kept vanishing. This wave after wave of loss was the critical period where trauma permanently wired his developing brain. Following his mother's death, young Jöns was sent to live with his maternal uncle, Magnus Justine. To say he was unwelcome is a massive understatement. It was a remarkably hostile, psychological nightmare. His uncle's wife struggled with severe, documented alcoholism, something without support systems back then. And they already had 7 children running around a chaotic, completely disorganized household. Berzelius was dropped on their doorstep and treated not as family, but as an extra mouth to feed, a massive burden they made sure he felt every single day. Imagine the mind of an 8-year-old with absolutely zero agency, living in a world that has proven to be entirely unpredictable, harsh, and fundamentally unsafe. The adults are dead, resentful, or incapacitated by addiction. To survive without breaking down, some children act out violently, while others withdraw into fantasy worlds. But Berzelius did neither. He didn't retreat into imagination. He retreated into hyper-reality, to literally pay his own boarding fees so his aunt and uncle wouldn't throw him onto the street. He began doing grueling rural farm labor during his school vacations. We are talking about heavy agricultural work for a child, sleeping in unheated storage rooms, living like a hired farmhand. But his real psychological escape, his safe space, was obsessively categorizing the natural world. He didn't walk in the woods to play. He worked, collecting insects and plants with clinical intensity. By the time he was a teenager, he had collected, identified, and meticulously cataloged over 369 distinct insect specimens. 369 insects. How does a child with zero control over his domestic tragedy cope? By finding a microscopic corner of the universe that he can master. He couldn't fix his aunt's alcoholism or bring his parents back, but he could take a chaotic, buzzing swarm of insects in a Swedish meadow, pin them to a board, assign them a Latin name, and force them into a perfect logical hierarchy. This was an absolute survival mechanism, literally building the neurological pathways and the cognitive foundation for his future obsession with chemical stoichiometry, the underlying math of how elements combine. It is terrifying how easily he could have slipped through the cracks. When he attended the cathedral school in Linköping, the faculty completely wrote him off. His teachers evaluated his academic performance and literally labeled him a slacker who possessed poor manners and is of uncertain promise. The man who would go on to analyze thousands of chemical compounds by hand, working 16-hour days for decades, was called lazy by his high school teachers. Why? Because he completely ignored his mandatory theological studies. His family and the school wanted him to follow their clerical footsteps, but he sat in the back of the classroom and ignored them completely. He wasn't slacking. He was exhibiting extreme hyperfocus on the empirical world, the things he could touch, measure, weigh, and observe. Religion had offered him absolutely no protection in his early life. Why trust a divine plan when that plan took your parents away? The physical world, however, obeyed strict rules. So how does an alienated, rebellious teenager, sleeping in storage rooms, break into the elite, closed-off gates of European science? His only practical backdoor was medical school. In the late 18th century, medicine was the accepted trade school for aspiring natural philosophers who needed financial stability to study chemistry and botany. He entered Uppsala University in 1796 to study medicine, primarily to get access to a laboratory. But poverty hit again, lacking a safety net. He lost his meager scholarship and had to drop out temporarily just to survive. He took a job as an apprentice at a pharmacy in a town called Vadstena. Seemingly a massive step backward, yet it became a crucial turning point. In that pharmacy, he learned a highly specialized, intensely physical skill, glassblowing. To run a new experiment back then, you had to physically breathe life into the glass apparatus yourself. You had to master the material properties of silica, the heat of the furnace, and how glass expands so it wouldn't shatter in your face while containing highly corrosive acids or expanding gases. By mastering glassblowing, Berzelius gained complete physical independence. He wouldn't have to rely on expensive imported German or French equipment. He could build his own scientific instruments from raw sand and fire. Scraping together money, He got his scholarship back and returned to Uppsala, turning his tiny windowless closet of a dorm room into a makeshift, glowing, sparking laboratory. Imagine the sheer sensory overload and extreme danger. A poor medical student generating volatile, highly flammable gases in a poorly ventilated closet, famously recreating the experiments of Carl Wilhelm Scheele by isolating oxygen. Then, right at the turn of the century in 1800, Alessandro Volta announced the invention of the electric pile, what we universally call the battery. It was the very first time humanity had a continuous, reliable source of electrical current. Berzelius immediately built his own, stacking alternating discs of copper and zinc separated by brine-soaked cloth, creating a primitive, sparking pillar of electricity right in his dorm room. But he still needed a medical thesis to graduate in 1802. He wrote a wildly experimental thesis, deciding to use galvanic, sustained electric shocks to treat human diseases, reasoning that if electricity animated muscle tissue, like Luigi Galvani had famously demonstrated by making dead frog legs twitch, perhaps a continuous current from a voltaic pile could cure deep ailments. He tested this on live patients suffering from paralysis, severe varicose ulcers, and St. Vitus's dance, a terrifying condition causing uncontrollable thrashing. It was an absolute, unequivocal clinical failure. The continuous shocks did absolutely nothing to cure their diseases. Yet, this miserable failure was the luckiest break in the history of chemistry. If it had worked, he would have spent the rest of his life running an elite electrotherapy clinic for the aristocracy in Stockholm, completely lost to basic science. Instead, forced to pivot his attention away from the biological results, he looked closer at the electricity itself. While passing currents through organic tissues and saline solutions, a profound realization cemented itself in his mind. He noticed how the electrical current systematically separated the chemical components. He realized with absolute, shocking clarity that electricity and chemical matter are fundamentally, inextricably linked. The force that makes a spark jump is the exact same force that holds a molecule together in a solid state. In 1802, before anyone truly understood the electron, this was a shattering paradigm shift. It was the conceptual seed of everything he would accomplish, the literal precursor to our understanding of ionic bonding. He graduated from Uppsala with a medically useless thesis, but armed with a profound, foundational chemical truth, ready to bend the chaotic universe to his will. Armed with a profound foundational chemical truth, Berzelius moved to Stockholm, but he was still practically penniless. He took a job as a physician for the poor, receiving almost no pay, walking the grim, destitute slums of the city. It was a bleak existence, until the trajectory of his life pivoted once again. He crossed paths with Wilhelm Hisinger. Hisinger is a crucial, often wildly underappreciated figure in the Berzelius narrative. He was a wealthy mine owner, a Swedish aristocrat with a deep, abiding passion for mineralogy and chemistry. Most importantly, Hisinger possessed the enormous capital and a fully equipped, state-of-the-art laboratory that Berzelius desperately needed. Recognizing almost immediately that this impoverished, intense, hyper-focused young doctor possessed a once-in-a-generation intellect, Hisinger essentially handed Berzelius the keys to his laboratory. Simultaneously, Berzelius managed to secure a position as an unpaid professor at the medical college, the very institution that would eventually evolve into the world-renowned Karolinska Institute. Because he was now teaching students, he decided he needed a proper textbook. But as he attempted to synthesize all the accepted chemical knowledge of the early 19th century into one cohesive volume, he hit a massive structural wall. The existing data on chemical compounds was a complete, unmitigated disaster. It was hopelessly inconsistent. A highly respected chemist in France might publish a paper claiming a certain compound was 40% oxygen, while an eminent chemist in England claimed the exact same compound was 48% oxygen. There was no standardized measurement protocol, no rigorous analytical baseline, just an incredible amount of sloppy laboratory work being accepted as fact. For a man whose childhood trauma drove a desperate need to organize chaos, this inconsistency must have offended him on a deep, existential level. He simply could not write a textbook based on contradictory data. So, he decided he had to weigh the entire universe himself. Berzelius embarked on an obsessive quest to definitively prove the law of definite proportions, the fundamental principle that chemical compounds aren't just arbitrary, randomized mixes, but that they always combine in exact, fixed, mathematically predictable ratios by weight. Over the next decade, utilizing a primitive mechanical brass balance scale, Berzelius conducted over 2,000 separate, extreme precision chemical analyses of more than 100 different chemical compounds. He performed this grueling labor largely by hand. He purified raw reagents, boiled them down, and filtered them. He waited hours, sometimes days, for a wet sample to dry completely over a flame. He transferred microscopic amounts of powder from one glass vessel to another, without losing a single, solitary grain. The sheer repetition and unimaginably tedious labor would have broken a normal person's spirit. But for Berzelius, this laboratory was his sanctuary. It was the ultimate expression of control over a chaotic world. The results were staggering. He calculated the atomic weights of the elements with frightening accuracy. For example, deriving the weight of chlorine as 35/45, almost exactly the modern accepted value. This level of precision allowed him to definitively settle the raging scientific debates of his era, most notably destroying Prout's hypothesis. Proposed by the English chemist William Prout, the highly seductive theory claimed that all atomic weights were simply neat, whole number multiples of hydrogen. If hydrogen was 1, carbon must be exactly 12, oxygen 16, and nitrogen 14. Many chemists desperately wanted Prout's hypothesis to be true because it implied a divine, clean, almost musical architecture to the universe. But Berzelius looked at his 2,000 painstakingly derived measurements and refused to play along. He boldly stated that chlorine wasn't 35 or 36, it was 35/45. He refused to round the numbers to make the theory aesthetically pleasing. By accepting the ugly decimals, Berzelius forced science to deal with the messy reality of nature, pointing the way toward the much later discovery of isotopes. However, history has a bad habit of romanticizing the lone genius toiling away by candlelight. The staggering volume of his output was impossible for one person to manage alone. We must shine a light on one of the most vital, historically overlooked figures in this story, Anna Sundström. From 1808 to 1836, for nearly 3 decades of his most productive period, Berzelius's laboratory was managed day to day by Sundström. Originally employed as his housekeeper, she quickly transitioned into his primary laboratory assistant and co-worker, and is rightfully recognized today as the first female chemist in Sweden. Managing a 19th century lab wasn't just sweeping floors. Anna Sundström actively managed the purification of toxic chemicals, meticulously cleaned the incredibly intricate, fragile glassware to prevent cross-contamination, and prepared the highly sensitive apparatuses. It was her rigorous, dangerous management that generated the sheer volume of accurate data needed to prove Dalton's atomic theory and establish stoichiometry. The men wrote the theoretical papers and got their names etched into the laws of physics, while the brilliant women, who frequently managed the physical execution of the science, were dismissed in official records as mere housekeepers. A profound historical injustice. With the elements weighed and the exact proportions verified, Berzelius encountered another massive structural roadblock. The actual written language of chemistry was completely broken. John Dalton, the famous English pioneer of atomic theory, had developed a system of notation using complex, circular pictographs. An oxygen atom was an empty circle. Hydrogen was a circle with a tiny dot in the middle. Sulfur was a circle with a cross drawn through it. Writing the formula for a complex molecule was like drawing a sprawling constellation of intersecting, shaded, and dotted circles. Economically and practically, it was a disaster. Printers didn't have movable typefaces for Dalton's complex shapes. They had to carve expensive custom wood blocks for every single chemical equation, drastically slowing down the dissemination of knowledge. Dalton was trying to represent physical, spatial reality, drawing what he imagined atoms looked like. Berzelius, the supreme pragmatist, realized that chemical notation shouldn't be a picture. It needed to be an algebraic abstraction. He simply hacked the printing press, Berzelius based his entirely new system on the Latin names of the elements. He created an elegant rule. Take the first letter of the Latin name, and if there is a conflict, add the second letter. Thus, cuprum became Cu for copper. Ferrum became Fe for iron. Plumbum became Pb for lead. Natrium became Na for sodium. And hydrogyrum became Hg for mercury. Crucially, he introduced the use of superscript and subscript numbers to show proportions, giving birth to the elegant simplicity of H2O. John Dalton absolutely hated it. Trapped in his own paradigm, Dalton fiercely resisted, complaining that Berzelius's letters were like Hebrew to him and obscured the physical reality of the atoms. Berzelius ruthlessly shot back in public, calling Dalton's symbols horrifying and utterly impractical. Berzelius's alphabet won out because it was vastly superior, cheaper to print, and easily communicable across language barriers. Armed with this universal language and a laboratory capable of unmatched precision, Berzelius and his team went on an unprecedented hunting expedition, searching for entirely new, unseen elements hidden in the rocks. When analyzing a mineral, the constituent parts are supposed to add up to exactly 100%. If the math yielded 99, 5%. Most 19th century chemists chalked it up to spilled powder or experimental error, wrote down 100, and went to the pub. But to Berzelius, that missing 0.5% wasn't a mistake. It was a fingerprint at a crime scene. It was empirical proof of undiscovered worlds hiding in the margins. This relentless pursuit led to historic discoveries. In 1803, working alongside his patron Hisinger, he discovered cerium. In 1824, through incredibly complex isolation techniques, he was the first to successfully isolate pure silicon, followed by zirconium. In 1828, while analyzing a dense mineral from Norway, he discovered a highly radioactive element and boldly named it thorium, after Thor, the Norse god of thunder. Naming the fundamental building blocks of the universe after pagan gods was an ultimate power move. But his most visceral discovery occurred in 1817. Berzelius was analyzing a red sludge from the bottom of a lead chamber at a sulfuric acid plant he co-owned in a Swedish town called Gripsholm. The sludge had a distinct, overpowering characteristic. It smelled strongly of rotting radishes. Initially, because of the smell, he assumed it contained tellurium, a known element named after tellus, the Latin word for earth. But his uncompromising analytical math proved the atomic weight didn't match. It was a brand new sister element, which he brilliantly named selenium, after Selene, the Greek goddess of the moon. The physical reality of working with selenium, however, was horrifying. The rotting radish stench of these compounds was so potent, it seeped deeply into his clothes, his hair, his skin, and his breath. The smell was so vile that his friends actively avoided him, refusing to invite him to dinner parties. This highlights the extreme bodily danger of early science. Chemists in the 1800s didn't have mass spectrometers or high-tech fume hoods. They used their own bodies as the primary analytical instruments. They used their noses to detect volatile gases and literally tasted unknown, newly synthesized salts to determine their properties. They put their very nervous systems on the line for data. Through this dangerous hands-on engagement, Berzelius possessed immense power in naming the world. He coined foundational terms still used by every modern student. Catalysis, the idea that a substance can speed up a reaction without being consumed. Isomerism, the realization that two molecules can have the exact same atoms, but totally different properties based on spatial arrangement. And allotropy, the concept that a pure element can exist in different physical forms. And perhaps most significantly, in an 1838 letter to his Dutch colleague Gerardus Mulder, who was studying complex nitrogen-heavy molecules in living tissue, Berzelius suggested a new term, deriving it from the Greek word proteos, meaning primary or standing in front. He gave us the vocabulary for the very machinery of life itself. He suggested these vital molecules be called proteins. But this immense, unprecedented string of successes was about to create a monster. Having invented the alphabet of chemistry and weighed the elements, Berzelius began to believe that his own theories were absolute, unshakable, divine laws of nature. and when the universe refused to obey his rules, the ultimate tragedy of his life would unfold. This brings us to the absolute core of his theoretical empire, the concept of electrochemical dualism. Based on his early experiments with the voltaic pile, where he saw electricity physically split salts apart into distinct components, Berzelius proposed a grand unifying theory of all matter. He stated that all chemical compounds are formed by two opposing parts, one electropositive part and one electronegative part. These two halves are attracted to each other exactly like magnets, and they combine to neutralize each other's charge. For inorganic chemistry, for your rocks, your minerals, and your basic salts, this theory worked perfectly. It was a brilliant, elegant way to explain why sodium, which is highly positive, bonds so violently with chlorine, which is highly negative, to make stable table salt. It made perfect mathematical sense. He was so incredibly successful at explaining the mineral world that it elevated Berzelius to an almost godlike, untouchable status in the global scientific community. In 1818, he became the perpetual secretary of the Royal Swedish Academy of Sciences. In this powerful role, he started publishing the Årsberättelser, the annual reports, where he meticulously reviewed, summarized, and critiqued literally all the chemistry being published in Europe. He became the ultimate gatekeeper of scientific truth, essentially acting as the supreme court of chemistry. If Berzelius praised your paper in his annual report, your career was made. You would get funding and university chairs. But if he criticized you, or worse, if your empirical data contradicted his established theories, he would systematically, publicly destroy your reputation. He had become the absolute chemical dictator of Europe. But then, a massive crisis emerged that his rigid theories simply could not contain. An entirely new frontier of science began to open up. Organic chemistry, the chemistry of carbon and living things. A brilliant French chemist named Jean-Baptiste Dumas conducted an experiment that absolutely shattered Berzelius's beautiful dualistic world. Dumas demonstrated a phenomenon he called substitution. Through rigorous laboratory work, he took acetic acid and proved empirically that you can take electropositive hydrogen atoms out of the molecule and swap them with highly electronegative chlorine atoms without destroying the fundamental structure or nature of the molecule. According to Berzelius's electrochemical dualism, this was mathematically and physically impossible. You cannot replace a positive magnet with a negative magnet and expect the structure to hold together. The charges would repel, and the molecule would tear itself apart. It completely violated the absolute core rule that Berzelius had built his entire 40-year empire upon. So, how does the ultimate empiricist, the man who spent a decade proving the law of definite proportions with raw, unassailable data, react when faced with undeniable empirical data from Dumas that contradicts his pet theory? He loses his absolute mind. Instead of adjusting his theory to fit the new data, which is the fundamental definition of what a scientist is supposed to do, he ruthlessly attacked Dumas. He used the full weight of his institutional power to attack the new, unitary theory of organic chemistry. He used his annual reports to write increasingly convoluted, absurd, mathematically desperate formulas, trying to forcefully bend the reality of organic chemistry to fit his old, inorganic rules. This is the tragic, psychological climax of his life. We have to look all the way back to the traumatized boy shivering in the storage room. He had escaped the unpredictable, terrifying chaos of his childhood by enforcing rigid, unyielding rules on the physical universe. Electrochemical dualism wasn't just a scientific theory to him. It was his psychological armor. It was his ultimate proof that the universe made sense, that it could be controlled. And now, the universe was acting chaotic again. His ego and his deep-seated childhood trauma simply wouldn't let him accept the messy, flexible, separate rules of covalent organic bonding. The ultimate tragedy here is that his dualism theory was actually a brilliant, necessary precursor to our modern understanding of ionic bonds. He wasn't entirely wrong. He just couldn't accept that his theory wasn't the only rule governing the universe. This dispute raises a massive question about the sociology and progression of science. What happens to a field of study when the greatest mind in it, the person holding all the institutional power and controlling the journals, becomes a roadblock to the truth. There is a famous, cynical saying by the physicist Max Planck: "Science advances one funeral at a time." Berzelius, in his later years, perfectly and tragically embodied this quote. He transitioned from a revolutionary visionary who tore down old paradigms into a bitter, conservative dictator, actively holding back the next generation of brilliant chemists like Dumas and eventually Pasteur. It is the ultimate tragedy of the brilliant mind. You build a magnificent cathedral of logic, and then you refuse to let anyone add a new wing to it, even if they have the perfect blueprints. And while he was waging this bitter, public, ultimately losing war behind closed doors against the academic journals, his own organic body was failing him in a way that is almost too poetic to be real. For decades, Berzelius lived a Spartan monk-like existence. His living quarters were basically just extensions of his laboratories. He had no real personal life outside of chemistry, no family of his own until he was 56 years old. At 56, he finally decided to seek some domestic companionship and married Elizabeth Papias, the 24-year-old daughter of a prominent Swedish cabinet minister. This marriage was a huge societal event in Stockholm. On his wedding day in 1835, King Charles IV, John actually elevated Berzelius to the rank of baron. It was the ultimate social triumph. The unwanted, impoverished orphan who slept in barns was now Baron Berzelius, rubbing shoulders with royalty. By all historical accounts, Elizabeth cared for him deeply, bringing him the domestic peace, love, and stability that he had been so cruelly robbed of as a child. But this domestic tranquility arrived far too late to save his failing body. Remember the rotting radishes? Remember the windowless closet lab in Uppsala? Decades of literally tasting unknown, newly synthesized chemicals, breathing in toxic elemental vapors, and working day and night in poorly ventilated spaces, saturated with lead, mercury, and volatile acids had taken their toll. It utterly, irreparably devastated his physiological health. The symptoms he suffered in his final years were horrific. He suffered from severe, blinding migraines that would leave him incapacitated for days. Interestingly, in his relentless, lifelong pursuit of pattern and order, he initially tried to tie these unpredictable migraines to the phases of the moon, desperately trying to find a rational, astronomical cause for his chaotic pain. He also developed crippling gout that eventually destroyed his mobility and forced him into a wheelchair. The very science that saved him from poverty, the science that elevated him to a baron, was literally poisoning his nervous system from the inside out. The ultimate tragedy, the scene we started this entire story with, was his cognitive decline. He suffered from profound depression and, worst of all, severe, devastating memory loss. The irony is absolutely shattering. This is the man who invented the system of classification we still use today. He organized the infinite chaos of the chemical universe into a neat alphanumeric language. He brought order to matter, but at the end of his life, his physical brain, damaged by the heavy metals and toxins he had studied so relentlessly, could no longer parse that language. Confined to his wheelchair, he would sit in his lab, look at the hundreds of bottles he had meticulously categorized over a lifetime, and he simply couldn't remember what the labels meant. Because he was a man of ultimate precision, a man who abhorred chaos above all else, he knew that an unlabeled chemical, an unknown variable in a laboratory, was infinitely worse than having no chemical at all. It represented the absolute return of chaos. Unable to trust his own failing mind, he was forced to systematically destroy his own precious samples. He poured them out. He smashed the glass contents. The great categorizer was erasing his own categories because the biological system in his mind had finally collapsed. Jöns Jacob Berzelius died on August 7, 1848. It is a Wagnerian tragedy of the highest order. But even as his mind faded and his physical, tangible samples were destroyed, the abstract architecture he built, the precise formulas, the verified atomic weights, the universal vocabulary, was already deeply, permanently embedded into the foundation of global science. It survived him. His arc is almost unbelievable. From a traumatized, unwanted orphan sleeping in rural storage rooms to the absolute, unyielding architect of modern chemistry. Every single time you look at a periodic table, every time you read a chemical formula like CO2, every time you hear a nutritionist talk about protein, you are interacting directly with the ghost of Jöns Berzelius. He wrote the operating system for how we understand the physical world, but studying his life leaves us with a deeply provocative philosophical tension. It forces us to ask, does the history of human progress rely more on the wild, chaotic innovators who break the rules, like Dumas, proving substitution against all established dogma? Or does it rely on the stubborn, dictatorial organizers like Berzelius, who force the chaotic world into a rigid system we can all actually understand and communicate with? Was his later dogmatism, his dictatorial ego that actively held back organic chemistry, simply the inevitable tax we had to pay for his earlier brilliant organizing genius? Could we have ever had the precise universal language of chemistry without the stubborn, trauma-driven obsession of the man who created it? It is certainly something to mull over the next time you write down H2O. If you enjoyed unraveling the complex, brilliant, and deeply tragic life of Jöns Berzelius with us, please make sure to subscribe, like, and share this video. Leave a comment down below letting us know which of his element discoveries surprised you the most. Was it the radish-smelling moon element, or the Norse god of thunder? Join us next time on Legendary Lives Unveiled as we continue to explore the dark, mysterious source material behind the figures who shaped our world.